Hello everyone, and welcome to part 1 of the tutorial on optimizing I/O in scientific applications. My name is Ritu Arora, and I'll be the instructor for all the 3 parts of this tutorial. This tutorial is being delivered as a part of my Better Scientific Software Fellowship. In part 1 of this tutorial, I'll present a high-level overview of why and how we should optimize I/O. I will also cover some general I/O strategies that can be useful while working on HPC platforms. I'll then present an overview of the Lustre parallel file system. In part 2 of the tutorial, we will go over the parallel I/O patterns and an introduction to MPI I/O. In part 3 of the tutorial, we will go over I/O in the context of checkpointing and AI. Every useful scientific application does some type of input or output. Such applications could be reading initial conditions or datasets for processing, or could be writing numerical data from simulations, or could be writing checkpoints every so often to be used in the event of any hardware failure. There are two main reasons due to which we should consider optimizing I/O. The first reason is that we should be reducing the overall execution time of our applications, and in doing so, we will likely reduce the associated computation costs, if any. And we want to reduce the burden on the shared high-performance computing or HPC systems on which our jobs may be running. In the case of serial applications, let's say, the total execution time is calculated as the time spent in the computation itself and the time doing the I/O. In the case of distributed or parallel applications, the total execution time can be broken down into 3 components: time taken for communication between the processes engaged in doing parallel computation, time taken for the computations themselves, and the time taken for doing the I/O. Hence, in both serial and parallel applications, it is important that we optimize I/O to reduce the overall execution time of the applications and enhance their performance. However, it is often seen that optimizing I/O is an afterthought. When we are working on shared computing systems, it is very important that we also know that there are certain patterns of I/O from the compute jobs that can stress out the file systems. Due to certain stressful I/O activities, depending upon the file system and its failover mechanism, the file system can become unavailable for the entire user community. Hence, it is very important that we are aware of how we are doing the I/O from our applications and do it optimally for not only enhancing the application's performance, but also for maintaining good citizenship on the shared computing platforms that we're working on. Let us look at some examples of inefficient I/O observed in serial and parallel applications. We have seen that oftentimes people open and close files inside loops. They've also observed that there is large-scale reading and writing to the shared file systems directly from the jobs that are running on the HPC systems. And then we've noticed that people could be calling I/O functions every time a value needs to be read from a file. We've also seen that certain APIs, algorithms, or methods chosen for implementing certain logic is not optimal or not the best option. And then we've also seen that there are attempts to access the data sets on a different system, which could be a secondary or tertiary storage system, from within the compute jobs while they are running. Let us review some solution strategies for each of the examples of inefficient I/O that we went over in the previous slide. Now, instead of opening and closing files inside a loop or inside loops, one can open the files before the loops, do the reading and writing inside the loops, and then close the files after the loops. Note that when you have nested function calls, where a function gets called in the loop, it is important to find the right level of nesting at which the file should be opened and closed, especially when you're implementing features such as logging or checkpointing. It is also important to review the user guides of the large-scale HPC systems of interest to learn about their hardware architectures. If a system supports a sufficient size of storage on the compute nodes or servers, maybe as a /temp space, then instead of directly reading and writing to the shared file systems from the compute jobs, you can evaluate if it is possible to do the I/O from the memory or from the temp space of the compute node or server. Reading and writing data from storage space available on the node can be significantly faster than reading from a file system. Now, please note that if you adopt this approach, as in if you're doing the I/O from memory or from the temp space, you might want to remember to copy your output files or the data from temp space to the file system before your job ends. Because once your job ends, you will not have access to the temp space any longer. Third strategy or idea I would want to mention is about calling an I/O function every time a value needs to be read from a file can cause performance penalties. Hence, if possible, read the entire file into an array and then work with the array instead of opening and closing the files every time you need the data. Additionally, please note that instead of reading line by line from the file, you could evaluate if reading blocks of data from a file would be possible and if it would be efficient. As an example, you can consider using fread in C to read more than a line in a single I/O call instead of using fgets that reads only, for example, one line at a time. It is important that we compare the performance of different functions, methods, or APIs by writing simple use cases before using them in the actual code. Because the choice of suboptimal functions, methods of APIs, or algorithms for a task will most likely lead to suboptimal performance. And please note that even if the compute jobs running on an HPC system can access large-scale data sets on a separate storage system, which could be your secondary or tertiary storage, the network bandwidth and latency that's involved can negatively impact the performance of your jobs and applications. To avoid this situation, it is recommended that you copy the datasets to the HPC system of interest prior to running the jobs there. And once the processing is done, you might want to copy the results back to the storage systems of your choice. Also, when you're working with large directories, note that at times running even ls command in a very large directory containing millions of files could suffer from performance issues. So it's important that you split large directories into smaller ones and compress those directories before your data transfer begins. Additionally, you can consider using rsync protocol or rsync tool with appropriate flags to transfer data from source to destination, especially if they are geographically disparate locations. Because the way rsync works is it works by copying deltas or differences between the source folder and the destination folder. So if in case there is an interruption in the internet service, for example, so rsync is going to help you resume the service or the data transfer from where it stopped rather than copying over everything from the beginning. Let us now review the concept of buffering in general and how it is applicable to optimization. So a buffer is a temporary storage area associated with input and output devices. It is important to understand the I/O buffering options supported by the programming languages and platforms that we are working on. To begin with, let us look at this example C program here on the slide. So this program prompts the user for entering two values, and then it calculates the sum of those two values and prints that sum to the screen. That's all this program does. In the first attempt of running this code, if you notice on the slide, I entered the two values 3.1 and 4.2 for A and B when I'm prompted for those. And then I see the value of sum printed as 7.3 on the screen. In the second attempt, though, of running this code, I enter more than one values when I'm presented the first prompt. The first prompt is for enter the value of A. Instead of entering just one value, here 3.1, I enter two values. I enter 3.1 and 4.2. The output, if you see from this code, is still correct. The code did not wait for me to enter the value of B. So the way it worked is, when we passed more than the required number of values, those extra values were held in a place called input buffer. And then the value from this input buffer was passed on to the next prompt automatically as input. Hence, when the program wanted the value of B, it just read it directly from the input buffer rather than waiting for my input from the command line. Therefore, I get the correct sum. 3.1 plus 4.2 is 7.3, and I get the correct sum printed on the screen. Now that we have understood the concept of buffering, let's delve deeper into this concept in the context of the C programming language. In C, stdioh is the standard IO library, and it supports buffering of data to reduce the number of read and write system calls to the operating system kernel by calling setBuff or setvbuff functions with appropriate parameters. Please note that the setBuff function is deprecated, and going forward, you might want to consider using setvbuff function. The setvbuff function allows the user to control the buffer associated with the stream, including changing the buffer size, flushing the buffer, changing the buffer's type, or even deleting the default buffer in the stream. Please note that you may call the setvbuff function only after the file has been successfully opened and before any file IO operations have taken place. The setvbuff function accepts 4 parameters. You can see the signature of this function on the slide. The first parameter is the file stream to set the buffer to. The second parameter is the pointer to a buffer for the stream to use. The third parameter here is the buffering mode to use. The buffering mode can be unbuffered, line buffered, or fully buffered. Unbuffered mode means that the output stream is unbuffered, and hence any data written to the output stream is immediately written to a file. In the line buffered mode, characters written to the output stream are buffered till a new line character is found, and at that point the data is written to a file. In the fully buffered mode, characters written to the output file are buffered till the buffer becomes full, and at that point the output is written to a file. And the last argument to this function setvbuff is size of the buffer. As per the C standard, the standard input and output should be fully buffered and standard error should be unbuffered by default. You might want to consider profiling the code on the platform of interest, and please check if full buffering and line buffering with appropriate buffer sizes are improving the performance or not. And in some cases, when large contiguous writes are involved, you might even consider turning off buffering to see if there are any performance improvements. Now let us look at the concept of using memory mapped IO, appropriate buffering, and their impact on the performance of the code. When a file is copied directly to the virtual memory or address space of a process via functions such as mmap in C, then the number of system calls for reading and writing are reduced, and this can enhance the application's performance. A C code for doing file IO could be involving the data transfer from a user-defined buffer, example from an array, to the stdio.h library buffer, and then from the stdio.h library buffer to the kernel buffer, and then from the kernel buffer to a file on the storage device. Hence, the data could be getting copied thrice between the program level to the storage level, and the system calls involved could themselves be incurring latency. Hence, by using memory mapped files, the buffer copies can be eliminated and the overheads of system calls and cache lookups, and hence the associated latency, can be reduced. Therefore, using the mmap function for large files can potentially improve the performance of applications, especially those involving random access, page reuse, and where data fits in the memory. Please note that for reading small files sequentially, using the read system call may be better than using mmap, and experimentation to find the best option amongst the two should be done. The memory mapped files can be accessed like arrays in programs, and only regions of files that are needed by the programs are loaded in the memory at any given point in time. The syntax of the mmap function is shown on the slide. It accepts the arguments such as follows. It accepts starting address for mapping. This argument provides the preferred starting address to use for mapping. Then it accepts the second argument, which is the number of bytes to be mapped, and it must be, or it should be, greater than 0. The third argument is the type of read-write execute access. This argument controls the type of allowed access to the pages. The predefined flags like prot_read could be used for read access. The prot_write is used for write access. The prot_exec is used for execute access. And prot_none is for no access. The fourth argument is about the flags to use. This argument determines whether or not the updates made to the mappings are visible to the other processes mapping to the same region. Some of the options or values that this flag can take are map shared, map private, or map fixed. The fifth argument is the file descriptor. This argument is a file descriptor representing the file that is meant to be mapped. And the sixth argument is the offset. The argument specifies the offset from which the file mapping should start. Please note that the mmap function returns 0 if it works successfully and returns map failed in the event of an error. On this slide, we see a very simple code in C whose purpose is to show how to use the mmap call. So this code does not necessarily demonstrate the benefit of mmap function call. It just demonstrates how to use it. And this code is available in my GitHub repository for the Better Scientific Software Fellowship Program. And the name of the file is memorymapped.c. So in this example, we have a file named inputfile.txt that we are opening in read and write mode. First, we create the file, and then we are mapping the file with the process. And then if you notice, we are using the map shared mode here, which means that the mapping will be shared with all other processes. Basically, all other processes that are shared to this object. It should also be noted that this function mmap, even though it is very powerful, it is only available or supported in the Linux environment. So if you have a code which has mmap function in it for performance reasons, please note that you might run into portability issues as well. Now let us look at I/O optimization in the context of AI frameworks. We know that large-scale I/O during the training of AI models can consume a significant amount of time and can pose bottlenecks during the pre-processing step. PyTorch, Keras, and TensorFlow are popular AI or machine learning frameworks. Let us review some techniques for optimizing I/O when using PyTorch, TensorFlow, or Keras. When you're working with TensorFlow, you can consider using prefetching or parallelizing data extraction. Prefetching is a technique that can be used to reduce the time in each training step by overlapping pre-processing with the model training such that when the model is executing a training step n, the input data is being read for the n+1th step. The prefetch transformation provided by TensorFlow.data API in TensorFlow can be used for prefetching the data ahead of its use, and then you can use auto-tune to decide at runtime about the amount of data to prefetch. Please note that overheads are involved in reading data from remote locations or serializing or decrypting the data, and hence the data should be copied locally. And then once it is copied locally, you can use the interleave transformation in TensorFlow to parallelize the data loading step. Now, talking about data loading, it should also be mentioned that when we are working with large data sets, it is not uncommon to see error messages related to insufficient memory on the CPU or GPU at the data loading step. In such situations, it can be useful to ingest data in batches and, if possible, in parallel. If you're working with PyTorch, then you can consider using asynchronous data loading by using multiple worker processes simultaneously and avoid out-of-memory problem during model training. There's a class called data loader that is available in PyTorch, which can be used for this purpose. By default, the setting for using the number of workers in data loaders is 0, and this should be changed for engaging multiple worker processes in loading the data while the main training process continues its execution. If you're using Keras, then you can also consider using data generators. You can use the default generators or write your own custom data generators with appropriate methods. The appropriate methods basically are evaluate generator, fit generator, and predict generator to use these data generators basically. I should also mention the concept of buffer checkpointing here. PyTorch supports buffer checkpointing, which is a technique that favors recomputing over storing inputs of all the layers of the AI model during the training step. By reducing the number of layers for which the input should be stored for computing upstream gradients during the backward propagation step and recomputing for others, the memory requirements are reduced, which in turn enables increasing the batch size. Now, the impact of increasing the batch size may vary from case to case. However, the API to use for buffer checkpointing is torch.utils.checkpoint API. Now let us review the concept of optimizing I/O in the context of parallel applications. There are multiple levels at which the I/O can be optimized for parallel applications. We can leverage the features or settings of the parallel distributed file systems that can provide parallel data paths to storage disks. We can consider using MPI I/O, or we can consider using high-level libraries like PHDF5 or PNetCDF. Please note that when we are using PHDF5 and PNetCDF, they support including metadata for describing the data stored in the files, and this is excellent. However, the applications that are built using these libraries will need additional software dependencies and will not be self-contained. So in this part of the tutorial, we'll be further focusing on file systems, and in the next part, we will be focusing on MPI I/O. Lustre, GPFS, and PANFS are some of the popular options for distributed parallel file systems. And here we will discuss Lustre. Lustre has a client-server architecture where the Lustre clients run on the compute nodes or the login nodes of the HPC system. And you can see them represented on the left side of this photo on the slide. And the servers run in proximity to the actual physical storage devices or volumes. And you can see them on the right side of this photo on the slide. This photo here shows the overview of the different components in Lustre architecture. Some of the key components that we would want to review with respect to the discussion on optimizing I/O are metadata server or MDS, metadata targets or MDTs, object storage servers or OSS, object storage targets or OSTs. The metadata server provides metadata services to the Lustre clients running on compute nodes or login nodes of an HPC system. It helps in looking up file names and providing information on directories, file layouts, and file access permissions. There can be one or more MDSs available in a file system. The metadata targets or MDTs are the storage devices used by a metadata server to store metadata. An MDS can be connected to one or more metadata targets. After basically receiving the file metadata from the metadata server, the Lustre clients connect directly to the object storage servers for file I/O. But at the very beginning, when a file I/O needs to begin, a Lustre client establishes the communication with the metadata server. Like I said, once It receives the metadata from the metadata server. The Lustre client then continues with the I/O by communicating directly with the object storage server. The object storage targets are devices which are used by the object storage server to store the contents of the files. An object storage server is often connected to multiple OSTs or object storage targets. The total storage capacity of a file system is the sum of the capacities of all its storage targets. Hence, the greater number of the OSTs, the better the I/O capability of a file system. It should be noted that an HPC system can have one or more Lustre file systems available on it, and each could be having a different number of OSTs. To check the number of OSTs available on the file systems connected on your HPC system, you may use the LFS OST command. Here on this slide, we are showing the output of running the LFS OSTS command. This command was run on the Stampede 2 system at the Texas Advanced Computing Center. This system has 3 file systems attached to it. One of the file systems is named as home, other is named as work, and the third one is named as scratch. So as we look at the output, it shows that there are 4 object storage targets associated with the home file system, 24 storage targets associated with the work file system, and 66 storage targets associated with the scratch file system. Lustre supports the striping of the files or chunking of the files across several object storage targets. A file can be split into multiple chunks or blocks of a fixed size such that each of these chunks can be stored on and accessed from different object storage target in parallel. Doing so increases the available bandwidth for I/O and provides the flexibility to overcome the storage limits that may be associated with any single OST. Typically, RAID 0 type of layout is adopted for a striped file, wherein a file is striped or stored across multiple OSTs in a round-robin manner. Here in this photo on the slide, we have a file named myfile, which is of size 12 MB. And if we want to stripe this file, the first thing we want to think about is how big should each of the chunk of the file be. So we are creating strips of this file or chunks of this file of 1 MB in size. Then we want to decide how many storage targets do we want to store this file on. And let's say we want to store this file on 4 storage targets. So when we say we want to store this file on 4 storage targets, that means our Lustre stripe count is 4. Basically, we will use 4 targets or storage targets to store a file. Because there are 12 segments or 12 chunks of this file, and as I mentioned, the arrangement of the stripes or chunks of this file on the OSTs would be in the round-robin fashion. So the first stripe of 1 MB goes to OST number 21 in this example. The second stripe of 1 MB in size goes to OST number 33 in this example. The third one goes to OST number 48. The fourth one goes to OST number 59, and so forth. So after we have stored the first 4 stripes or chunks on the 4 targets, then we will go in the round robin manner, and the 5th stripe or the 5th chunk here will be picked and mapped to the first OST in the series, which is OST 21, the next one to OST 33, and so forth. So that's how the striping works in the Lustre world. System administrators set a default stripe count, which is the number of OSTs across which a file is stored by default. And they also set a default value for the stripe size. Again, stripe size is the size of each chunk of the file that is stored on the object storage target. And all the newly created files on a file system by default follow these default stripe count and stripe sizes set by the system administrator. A cool thing about Lustre is that the users on an HPC system can check these default values by running the LFS getStripe command, and can reset the default stripe count or stripe size on their files and directories by using the Lustre LFS command. This slide shows the LFS get stripe and LFS set stripe commands in action. So we are running the command LFS get stripe on a file named test file. And we see that the stripe count is 1 and the stripe size is 1 MB. What we do next is we change the default values here. So here we are setting the stripe count to 4 with LFS set stripe -C flag. We are saying set the stripe count to 4, and with -S we are saying set the stripe size to 4 MB. And we are creating a new file called test file 2. Then when we run the LFS get stripe command on test file 2, we see that our stripe count has changed to 4 and our stripe size has changed to 4 MB. It should be noted here that the striping can be set at the directory level such that all the files created within the directory inherit the striping related settings on the directory. The desired striping related settings should be made before a file is created. When we move a file with the mv command, it will not change the striping related settings, but when we create a new file by using the copy command, then this new file will be able to inherit or get new settings for the striping value, whatever we set at a particular directory level or at the individual file level. It should be mentioned here that both understriping and overstriping should be avoided, as overstriping can result in writing small chunks to each object storage target, thereby underutilizing it. And understriping can lead to too much stress on a single OST. It should also be noted that there is an increased risk of file becoming unavailable if any of the OSTs on which the chunks are stored go down. However, as the HPC systems are meant for computing and not storage, this risk should not cause a problem in the long term, as the users are expected to move their output files to a secondary or a tertiary storage system anyway after their jobs complete running. Now let us consider a case study of Flash astrophysics code. With this code, we will demonstrate the impact of striping on the time taken for doing the I/O and the health of the general file system. So a few years ago, we had a user who was running the popular Flash astrophysics code. They were running Flash 4.2.2 on the Stampede system at the Texas Advanced Computing Center when the job stressed out the file system and the object storage servers became unresponsive. Upon investigation, it was found that the job involved reading a restart file or a checkpoint file once during running using 7,000 plus cores. After the restart step or reading the restart file, after every 10 minutes or so, the code was writing a checkpoint file. The restart file that was written initially was 250 GB in size and was written with the default stripe count of 2. Now all 7,000 plus cores were trying to read this single file, and this was so inefficient and it monopolized the two object storage servers so much that they were unable to respond to other requests and became unresponsive. To find a remedy for this situation, performance testing was done using the different Lustre stripe count settings on different output directories. The code was run on 7,620 CPU cores, and the size of the checkpoint file that was initially read was 189 GB. The data related to this testing is presented on the slide. As we can observe from this data, with the stripe count of 80, the time taken for reading the file was lowest, while with stripe count 40, the time taken for writing was lowest. However, we should note that the stripe count of 40 looks best in this scenario, as beyond that, even though the time for reading continued to decrease, but it decreased at a slower rate. However, the time for writing the checkpoint file increases noticeably in going up from stripe count 40 to 60. I should mention here that Flash can do both serial and parallel I/O. And users can forget to set the appropriate stripe count on the directories in which output files from Flash are written. Hence, it was important for us to update the Flash code for doing both serial and parallel I/O and set the appropriate stripe count on the files from within the code. So we ended up modifying 3 files in Flash code and either used the MPI infoset call, to which we passed hints for setting the Lustre stripe count, or we made the calls to LFS set stripe directly from within the code. We will see more about these options of calling MPI infoset function to pass Lustre hints in the part 2 of the tutorial. Now let's review some advantages and disadvantages of file striping. Advantages include that a file size is not limited to the space available on a single OSD, and the I/O bandwidth can be spread across multiple storage targets by placing strips of files on multiple storage targets. In this manner, the file's I/O bandwidth is expanded. The disadvantages are that, like I mentioned previously, this can increase the overhead due to the need to manage the file chunking, striping, network connection, and multiple OSDs. And like I mentioned before, this can increase the risk of a file becoming unavailable if any of the object storage target on which its chunks are stored go down. Here on this slide, I'm presenting some of the scalability information related to the Lustre storage system. So if you notice that the maximum stripe count that can be supported on Lustre is 2000, and the maximum stripe size that can be supported is up to 4 GB in size. Then depending upon the type of backend we use for Lustre, our file system size or the maximum file system size can vary from 512 petabytes to 8 exabytes. It should be noted that Lustre can be easily stressed out by certain activities. To maintain a good citizenship on the HPC system, having the Lustre file system, it is recommended that we avoid opening and closing the same file every few milliseconds from our compute jobs, as it can stress out the metadata server. Also, opening too many files too frequently can stress out both the metadata server and the object storage targets, and hence we should avoid this as well. We should also avoid creating thousands of files in the same directory. Coordinating access to several thousand files simultaneously or synchronizing their metadata from a single job can stress out the metadata server, and hence this should be avoided. Hence, it is recommended to break down large directories into smaller subdirectories when you're working on a Lustre file system. With that, we conclude part 1 of this tutorial. In part 2, we will be covering parallel I/O patterns and MPI I/O. Thank you for your patient listening. And if you have any questions about this topic, please feel free to reach out to me at any time.